There are three modes of heat transfer, like conduction, convection and radiation, but the basic modes of heat transfer are only two, conduction and radiation, and convection is a special case of conduction where there is a microscopic movement also, right. So we saw the mechanisms of we explained the mechanism, I explained the mechanism of conduction and heat transfer. Then we also looked at boundary layer theory, a very brief introduction of boundary layer theory and convective heat transfer, the concept of Nusselt number, that is the heat transfer coefficient, Nusselt number, Newton's law of cooling and all that. Anyway, we restrict our attention to conduction and radiation in this course, convection is not a part of this course. Now in this class we look at the importance of thermal radiation, why thermal radiation is important. A lot of you will have a general, everybody, most people have a general feeling that thermal radiation is important only when the temperatures are high, right. Generally when the temperatures are low we will say okay, radiation can be neglected, and okay, that is the argument generally put forward by many people, okay, who are not inclined to include radiation in their analysis for reasons best known to them. So we will just see, we will just take a simple example and see whether this assumption is justified, that is neglecting radiation in a heat transfer analysis. Then we look at the electromagnetic spectrum, and I will show you some pictures of electromagnetic spectrum and look at the various portions of the spectrum. We will solve one or two basic problems connecting wavelength, wave number, velocity, frequency and all that, and then we will start off with the definition of a black body and properties of a black body. So that will be the route we will be taking. So the importance of thermal radiation, basically the first point is Q conduction is proportional to delta T. Q convection is also proportional to delta T except for free convection. Correct? Why? Why this? Because Nusselt number is A Rayleigh number to the power of B for free convection. So this is A into some constant, okay. B is usually about 0.25, so therefore the Nusselt number goes as okay. So okay, so Q will go as delta T to the power of 1.25 for laminar natural convection flows. For turbulent natural convection flows it will go as 1 delta T to the power of 1.33, okay, fine. This Ra is the Rayleigh number. Acceleration due to gravity, isobaric cubic expansivity, which is for ideal gases we can equate it to 1 by T, where T is the temperature in Kelvin, delta T is the temperature difference imposed in the problem, L is your characteristic length, characteristic dimension, it could be length of a plate, diameter of a cylinder or diameter of a sphere, nu is the kinematic viscosity and alpha is the thermal diffusivity, okay. So the Rayleigh number, you can do a scaling analysis and prove that the Rayleigh number is a fundamental dimensionless parameter governing free convection much in the same way as the fundamental dimensionless parameter which governs force convection is basically Reynolds number, okay. So it will be actually many times it will be Reynolds number and Prandtl number, but Reynolds into Prandtl, if you combine Reynolds into Prandtl it becomes the Peclet number, it becomes the Peclet number, okay. The Rayleigh number can also be written as the product of GR into PR, where GR is the Grashof number, this can be written as okay. So this is GR, one scientist gets multiplied by the second scientist and becomes the third scientist. Okay, fine. Now you can see that Q convection is proportional to delta T. In convection you have to take it with a pinch of salt because it is delta T to the power of 1.25 for natural convection. So Q radiation is proportional to T to the power of 4. So a non-linearity enters the problem right away because Q is proportional to the difference in the fourth powers of temperature. The difficulty with radiation first stems from the fact that the radiated heat transfer is proportional to T to the power of 4 minus T infinity to the power of 4. Okay. So therefore its importance non-linearly increases with the increase in temperature. Okay. So at high temperatures, whether it is an IC engine or a boiler or furnace and all that, then it becomes inevitable that you will have to consider radiation in the analysis. If you are talking about a temperature of 1200 degrees centigrade or 1500 degrees centigrade, there is no escape from considering radiation. Radiation will be the dominant mode of heat transfer. Are you getting the point? In fact, in your boiler there is a radiant superheater section where the ultimate heat transfer takes place, where the temperature of the steam is lifted, right. In the steam drum the liquid is separated from the vapor and then you get steam at a temperature which is just above the temperature at which it changes phase. After that the superheating is done by the radiant superheaters. Or in a paint baking oven, if you want to coat some tubes or metal pipes, and then these are all invariably baked. Okay, even a microwave oven works on the principle of microwave oven. Basically there is radiative heating in the microwave region of the spectrum. So the importance of thermal radiation stems from the fact that the first point is Q is non-linearly varies with temperature. Number 2, radiation requires no material medium to propagate. So the proof of that is we receiving the solar radiation now as we receive the solar radiation now, which is coming from millions or billions of kilometers away. So it is ample proof that radiation is able to travel without a medium, that is radiation is able to travel through vacuum. The best part is radiation travels best in vacuum because there is no absorption or scattering, or once it enters the atmosphere all these activities start. There is absorption by certain molecules, then they again reflect, or we call it a scattering, which is because of which you get the blue sky, Raman scattering, for which he got the Nobel Prize, right. So there is scattering, there is absorption, and since all these molecules are also at a temperature greater than 0 Kelvin, as a consequence of the Prevost's law they also emit. So the atmosphere is emitting, absorbing and scattering. Are you getting the point? But outside the atmosphere the radiation is able to travel without any distortion at all. So radiation requires no material medium to propagate. Radiation can travel in vacuum also. Okay. Therefore, when you travel in your Shatabdi or Rajdhani Express, or when you are traveling by plane, when you are having a double pane window which is used to eliminate heat transfer, right, you get two glasses, okay, two glass plates, the gap in between. Have you seen in AC chair car compartment, there are two glass plates, in between there is a gap. You thought that you are very smart, you killed all heat transfer, you killed only convective heat transfer, you put air inside. Okay, so the convection is replaced by conduction, but however even if air is there, when the temperature is sufficiently large it will set up a natural convection. Forget for the time being that the gap is so small that natural convection does not set in, but these two glass plates are at some temperature, and in between even if there is vacuum there will be radiative heat transfer. Okay, so there will be radiative heat transfer in that situation. Are you getting that point? So radiation requires no material medium to propagate, therefore we cannot it is not easy to say that okay, under these media radiation is not important, we can neglect. Okay. Point number 3, even at low temperatures radiation may be significant. Let us consider a simple, let us consider an example. Let us take a vertical flat plate, let us say it is about, so L equal to 0.5 meter. This glass plate is maintained at 100 degree centigrade. Again, you do not ask me how it is maintained, somehow I am maintaining it 100 degree centigrade. Okay. Now outside is let us say 303. Okay. There is a heated plate which is standing in still or quiescent air. What will happen now? What will be the story of this plate? What will happen around this plate? Convection. What? Which convection? It is still air, natural convection. So a boundary layer will develop. So boundary layer will develop on both sides. Correct? Right? I will draw it here. I will keep this, right? By chance I wrote this. I am going to use this now. Huh? Let us say that the emissivity of the plate is also 0.9, that is, it is coated with a black paint. What is the definition of emissivity and how do you characterize emissivity? Is emissivity a function of length? Is emissivity a function of angle and all that will be a part of this course. But now for the time being, let us say that there is some average, there is an overall average emissivity which is characterizing the surface, right. Now the boundary layer will develop like this. The beauty of this boundary layer is, now the velocity is 0 here, the velocity is 0 here because it is still air. If it is 0 everywhere, if it is like this, then we have to go home, there is no convection problem. We know that there is a velocity very close to the plate, that is within the boundary layer, so it will go up like this. Okay, this is the velocity boundary layer, right. Okay. Now, what is the heat transfer coefficient in this? So we know that the Nusselt number is given by A into Rayleigh number to the power of B. So this is for A and B will change depending upon the configuration, whether it is a plate, cylinder, or whether it is laminar or turbulent. I will take a very simple well known correlation, 0.59 Rayleigh to the power of 0.2. I think it is a Sparrow and Greg's correlation. Maybe they did it in 1959 or so. Okay. Now let us use this. Let's calculate the Rayleigh number for this. Please switch on your calculators. Okay. So the Rayleigh number for this, based on the length L, G is 9.81, delta T is 70, beta basically the isobaric cubic expansivity 1 by T mean. Okay, so T mean did I make it 303? Okay. What is T mean? Good, 338 Kelvin. So we got G, we got beta, we got delta T, L is 0.5. I will give you the value of nu. Nu varies with temperature, but do not worry. Just go ahead and tell me the Rayleigh number. It has to be less than 10 to the power of 9 in order that it is laminar. If it is more than 10 to the power of 9, it will begin transition to a turbulent flow. Huh? 7 into 10 to the power of 8. Is it so high? Okay. Vikram, get it? Abhinandan, 7 into the correct. Okay. Now what is the Nusselt number? $99, $100, $105, how much is it? Please bring your calculators, otherwise you will waste time in the class. Every class we will solve a problem, more or less. 96, good. So Nusselt number is 96. So the Nusselt number is a dimensionless heat transfer coefficient. Nusselt number is given by HL by K. The K of air is about 0.03 watt per meter per Kelvin. So now what is the heat transfer coefficient? This is what I call as H bar, that is H average, that is the average heat transfer coefficient of the plate, because the heat transfer coefficient will vary from the leading edge to the top. It is an averaged out quantity. How much is Deepak? Whatever you do, you will get a value which is between 5 and 8. Yeah, because of if you get anything outside of this range for air for these temperatures, then you have made some mistake. So generally people will assume a safe this thing of 6 or 7 watts per meter square per Kelvin, even without doing the calculation. 5 point? Okay, 5.8. Okay, so now I taught you free convection in 20 minutes. This is how you approach a free convection problem, okay. Now the heat flux convection, let us worry only about one side, because both radiation and convection are taking place from both sides. Let us consider one side. So H A 5.8 into 0.5 into 1, right? Yeah, but the area is the same. Let us stick with the Q convection. How much is it? 400?
406.
Okay. So such type of calculations are also very profound, because the temperatures you are talking about 100 degrees is what is normally, in fact it is more than the reliable operating temperature of electronic equipment. Electronic equipment will work at about 80 or 85 degrees centigrade. So if you do all this Rayleigh number business, you are getting 406 watts per meter square. So let us say approximately you have some other situation where H can be 6 or 6.5 or something. The Q convection can touch about 500 watts per meter square. So you are talking about flux levels of half a kilowatt per meter square with natural convection. That is what is possible. If you are talking about a flux level in your equipment which is more than 0.5 kilowatt per meter square, you have to use a fan. The fan, you can also do calculations like this and find out what is the maximum capacity, what is the maximum flux which one fan can withstand. Then you make 2 fans, just like in your desktop you have 2 fans. After that, liquid cooling, jet impingement cooling, data center. I mean in data centers you cannot cool everything with fan. Okay, first the air itself will be conditioned there, it will be heavily conditioned. The data center will be maintained at 16 degrees centigrade, so that Q is equal to HA delta T. That delta T also you get an advantage. Then inside the computer you will have all cooling strategies. So you must, as engineers, you must have a feel for what is the flux level associated with natural, how much of flux can be dissipated using natural convection. So the ballpark or the approximate figure is more than half kilowatt per meter square you can't do. You can convert it into equivalent centimeter square, millimeter square and work out the numbers. Okay. Now the beauty here is what will be the Q radiation from the problem, for this problem. I assume that the sink for the radiation is the same as the sink for the convection, which is alright. So I assume that the walls of the room are at the same temperature as the ambient, which is a reasonable assumption. Sometimes these two may not be the same. Are you getting the point? To cut a long story short, T infinity for convection need not be the same as T infinity for radiation. Oftentimes we assume them to be the same. Okay. So sigma is the Stefan-Boltzmann constant. Yeah. So epsilon I gave 0.9. So T in Kelvin, watch out, huh? Don't put it in centigrade and the whole thing will cup. Okay. It is easy to remember this. 5, 6, 7, 8. Okay. 5.67, but you should know where the decimal place and put the minus. Huh? So that is a Stefan-Boltzmann's constant. Stefan guide, and Boltzmann was a student, I think. Or is it the other way? Yeah, I think. Stefan was a guide and Boltzmann was a student. Okay. So Stefan-Boltzmann constant is 5.61 10 to the power of minus 8 watts per meter square Kelvin to the power of 4. So Q radiation is, so Q radiation by Q total is how much? Point?
5.
Who says radiation is negligible at lower temperatures? The people who say this are the people who do not know heat transfer. But again this analysis has to be taken with a pinch of salt. Suppose I blow air, I have a fan, then the natural convection will become forced convection. Instead of 5 I may get a heat transfer coefficient of 15 or 20. Then what will happen is I may get a Q convection of 1 kilowatt per meter square or 1.2 kilowatt per meter square or 1.5 kilowatt. Even if the convection quadruples, that it becomes 4 times, if the flux level is 1.8, this fellow is 0.57, it is not negligibly small. So it depends on what radiation can be neglected only in relation to the other mode of heat transfer. What is the strength of the other mode of heat transfer? If it is convection in air, regardless of whether it is free or forced convection, radiation cannot be neglected. However, if it is water, then the story turns completely upside down. Water is also an absorber of radiation, you cannot do that simple analysis. If it is water, it has got such a terrific thermal conductivity of 0.6 watt per meter per Kelvin as opposed to air, but as opposed to liquid metal it is having a poor thermal conductivity. Air thermal conductivity 0.03 watt per meter per Kelvin, water is 0.6, immediately all these numbers will change because the Nusselt number is HL by K. Okay. So the KH will increase, so if it is water the radiation contribution will become very negligible. So if you are having air cooling, if you are doing a CFD analysis of a desktop or all this, we cannot neglect radiation analysis. Now thankfully even Fluent has radiation modules, many people use the combined analysis nowadays, their prediction of maximum temperatures or prediction of operating temperatures of electronic equipment. Okay. So this places things in perspective. So if it is natural convection or even in mixed convection where both natural and free convection are important, radiation may play a part, and radiation cannot often be neglected by simply putting the argument the temperature is very low. Again I will ask the question, how low is low? Okay, there is a reasonable temperature 80 to 100 degrees centigrade also radiation is important. Okay. Now let us go to the electromagnetic spectrum. So radiation travels, radiation actually there are two. So wave model and the quantum model. I told you that using the wave model you can characterize it with the wavelength, you can characterize with the frequency, speed and all that. E is equal to h nu and all those things which are applicable for optics is applicable, but the radiative properties of black body behavior could not be explained using electromagnetic theory, therefore the quantum theory had to be invented. Electromagnetic radiation travels with the speed of light, okay. So the C naught, that is the velocity of light in vacuum, you can consider the velocity of light in vacuum to be the velocity of electromagnetic radiation when it is passing through vacuum, 2.998. or approximately 3 into 10 to the power of 8 meters per second. C naught is the velocity in vacuum, okay. Now you can characterize nu frequency, correct, 1 by lambda wave number. If the velocity of light in a medium is c, okay, we know that c has to be less than or equal to c naught, okay. So c naught by c is equal to is the refractive index of the medium. Glass, what is the refractive index? 1.5, good. For gases, for air generally it will be very close to 1. We can say n is approximately 1 for gases. For vacuum it is 1.000 whatever, for other gases it will be slightly more, but it will be equal to 1, okay. Now we look at the electromagnetic spectrum. I will host it on Moodle, do not worry, but important things you can copy down, you do not have to take down every detail. If I am using a PowerPoint presentation, I will put that, I will host that PDF or PPT on Moodle, www.moodle.iitm, then you can go to courses ME6200 and click, you can use students, user ID and password, students and open it, and then you will be able to see, okay. Now let us look at the electromagnetic spectrum. There are various ways of characterizing it. One way of looking at it is through the wavelength, lambda. You can also look at it from frequency, or these two can be related to get an electromagnetic radiation of such a wavelength or such a frequency, what should be the temperature of a body which can emit radiation of this wavelength or frequency, okay. And this gives you the approximate size, the wavelength corresponds to what is the order of magnitude of the various things you encounter, okay. For example, radio waves 10 to the power of 3 meters wavelength, gamma rays at 10 to the power of minus 12, gamma rays have got a terrific frequency, right, what is that, 10 to the power of 20 hertz. The energy of electromagnetic radiation E is given by h nu, but we have to derive that, right. E is given by h nu, where h is the Planck's constant, 6.627 10 to the minus 34 joules second, okay. So now look at atomic nuclei, now look at these gamma rays have got a terrific frequency, therefore E is equal to h nu is very high. So they are all high energy radiation, so people who are dabbling in this are the high energy physicists. Bob Atomic Research Center, people are working on the collider, this thing, and people who are doing research. High energy physicists are interested in this. Okay, look at the other end of the spectrum where the frequency is very low, E is very small. This is used by electronics and communication engineers, where E is equal to very small, where E is very small. Therefore, they have to do modulation. There is a carrier wave, and then you modulate, then it is sent across, then it is demodulated, and mechanical engineers are somewhere in between this. The ECE guys are here, the physicists are here, we are here. Sometimes we are visible, sometimes we are invisible. Okay, so visible is 0.4 to 0.7, you are either in the ultraviolet or infrared. Why engineers are operating on this? Engineers are operating on this because this corresponds to the reasonable level of temperatures encountered in engineering applications. We do not have billions of Kelvin and all that, we do not do such type of experiments. The only time where we encounter that may be nuclear fusion or this thing, that is also taking place only in the lab. Generally we will talk about a temperature of 500 Kelvin, 800 Kelvin, 1000 Kelvin, gas turbine 1500 Kelvin and so on. So thermal radiation, lambda is 0.1 to 100 micrometer. This is of interest to the thermal engineer. Okay, this is of interest to us because you look at the temperatures, right, that yellow color is there, right. If you look at the temperature of bodies emitting the wavelength, this yellow color is of interest to us. Okay, so there are other ways of looking at the spectrum. This corresponds to basically the wavelength corresponds to what, these buildings, these atomic nuclei and all that, right. So I will put this up on, this is another way of looking at it, right. So radio waves, microwaves, these are used by electronics and communication people. Okay, gamma rays and X-rays are used by physicists. They can also be used for, X-rays are used, they can penetrate the flesh and they can give you information on the bones. Radiology and interventional radiology is okay. So these are basically of interest to the high energy physicists. These are of interest to the electronics and communication engineer. Now look at this visible. This visible is 400 nanometer to 700 nanometer. So that is 0.4 to 0.7 micrometer. So violet to red, right. So this is the spectrum. Now for us the 10 to the power of 0 meter, it is too big. Okay, so we do not talk about meter wavelength and all that, mechanical engineers. So we will say 10 to the power of -6. So that is a micrometer. What is this? Nanometer. 10 to the power of -10.
Angstrom.
Angstrom. So we either work with micrometer or nanometer or angstrom. Angstrom we don't, engineers don't normally use, physicists use, I think nobody uses angstrom now, right. We always talk about micrometers. Okay, so this is of interest to us. So that is why I am saying 0.1 to 100 is of interest to us. Okay, so these people will this one 400 to 700, they will divide it into 255 colors, right, depending on the resolution. In a camera they will put it into 255 colors. So as far as a thermal engineer is concerned, suppose I take a picture, okay, I can resolve the 255 colors, and then if I have a backup of a thermocouple measurements, I will correspond each of these colors to some temperature, and I can use a color map, as a code for getting the temperature. One of my students is doing PhD on this. There are sheets which are available. When you paste on a surface, if the temperature of the plate increases, its color will change. So this is called liquid crystal thermography. You can come to the heat transfer lab one day, anytime you can walk, you can talk to Pradeep Kamath, my student. There is a student called Konda Reddy who is working on liquid crystal. So we imported the sheets, so it is very nice. So you can get a full color map. So you have to take on a CCD camera, you take this picture, use an image processing software. So basically it will give a color picture. simultaneously you have a thermocouple and then independently measure the temperature, then you link up this color with the temperature, and in future if this is the color pattern, this is the temperature. Color can also be used. So in fact in measurements there is something called the color temperature, there is something also called the color temperature, okay, fine. Now this is as far as electromagnetic spectrum is concerned. Let us solve some two small problems and close for the day. So problem number 1. Problem number 1, radiation at a wavelength of lambda equal to 3 micrometer. Radiation at a wavelength of lambda equal to 3 micrometer travels through vacuum. Radiation at a wavelength of lambda equal to 3 micrometer travels through a vacuum into a medium. Radiation at a wavelength of lambda equal to 3 micrometer travels through vacuum into a medium with n equal to 1.4, that is refractive index equal to 1.4. A, determine the speed, frequency and wave number. A, determine the speed, frequency and wave number. A, determine the speed, frequency, wave number for radiation in vacuum. Determine the speed, frequency and wave number for radiation in vacuum. A, determine the speed, frequency and wave number for radiation in vacuum. B, determine the above quantities. B, determine the above quantities and also the wavelength. Determine the above quantities and also the wavelength for radiation in the medium. Determine the above quantities and also the wavelength for radiation in the medium. Just try this. So C naught A so 9.993 10 to the power of 13 second inverse, that is second to the power of -1, or you can also write it as hertz, okay. Is it clear? Blue is okay? Huh? It is not okay, no? White, okay. Now okay. So determine the speed, frequency, speed is this, determine the speed, frequency, wavelength, we have done this, okay. So the beauty is even when it changes from vacuum to medium, the frequency does not change, only the wavelength will change, okay. That is a funda there. So for part B, simple, just reinforces your concepts, that is all, okay. Everybody through with this? Problem number 2, the wavelength and speed of radiation. Problem number 2, the wavelength and speed of radiation, the wavelength and speed of radiation travelling within a medium, the wavelength and speed of radiation travelling within a medium are 3.2 micrometer, the wavelength and speed of radiation travelling within a medium are 3.2 micrometer and 2.3 into 10 to the 8 meters per second, or 3.2 micrometer and 2.3 into 10 to the power of 8 meters per second respectively. Determine the wavelength of the radiation in vacuum. Determine the wavelength of the radiation in vacuum. Same problem, I am restating it. How many different ways the same problem can be posed? That is the whole idea of this exercise, right? Determine the wavelength of the radiation in vacuum. Just take 2 minutes, finish it off, and then we will close for the day. Okay, so we will stop here.